Problem number 15. A mass M equal 100 gram is attached to the end of a string of length R equal 2 meters. A person swings the mass overhead such that their hand travels a circle of radius small r equal 3 centimeters at angular velocity omega equal 10 radians per second ahead of the mass m by an angle of pi over 2. Estimate the force of air resistance on the object. Solution for problem number 15. Let's draw free-body diagram for this process. On this picture we have tension in the string T, create angle between string and the big radius theta. It means that this tension in this direction must be compensated by force of air resistance, and we can count it. We have tension equal m omega square big R, and we have projection of tension in body motion equal tension multiplied by sine theta, which is approximately T small r over big R, which is m omega square small r. And after putting numbers we have 0.3 newtons. That's answer D, and that was solution for problem number 15. Problems 16 and 17. The following information applies to problems 16 and 17. A hoop of radius small r is launched to the right at initial speed v0 at ground level. As it is launched, it is also spun counterclockwise at angular velocity 3v0 over r. The coefficient of kinetic friction between the ground and the hoop is mu k. Problem number 16. How long does it take the hoop to return to its starting position? Solution for problem number 16. When the hoop is moving, it is slipping, and because initial speed was v0 to the right, and if the hoop is slipping till it will return to initial position, its velocity will be v0 to the left. It means that total change of velocity will be 2v0. And in that case, because acceleration due to force of friction is mu kg to the left, and the total time must be equal to delta v over a, which is 2v0 over mu kg. That could happen if our hoop is moving and slipping till it will reach the initial point. Now we need to count what will be angular velocity when it will return to the initial position. For rotation we have equation I alpha equal mu k m g r, where I is moment of inertia, alpha is angular acceleration, mu k m g is force of friction, and r is radius. So it means that on the right we have torque. Now we can count what is angular acceleration. For hoop we have moment of inertia I equal mr square, and we have angular acceleration alpha equal mu kg over r. So it means that total change of angular velocity equal alpha t, and after putting all these expressions we have 2v0 over r. It means that the final angular velocity will be initial angular velocity minus delta omega, which is v0 over r, and this correspondent with the velocity of this hoop to the left. It means that exactly in this initial position it will stop to slip. It means that we counted total time 2v0 over mu kg correctly. and that was answer B, and that was solution for problem number 16. Problem number 17. Would the answer to the previous question, namely the amount of time to return to the starting position, be the same for the uniform disk with the same coefficient of friction, plunged with the same initial conditions? Solution for problem number 17. Because for uniform disk we have moment of inertia I is 1/2 mr square, which is twice less than for hoop. We have angular acceleration is twice greater than for the hoop. It means that our disk will start to move without slipping earlier than for hoop. It means that it will spend more time to return to initial position. Correct answer is D. No, because the disk stops slipping too soon. That was a solution for problem number 17.